We want to determine the region in the xy plane for which this differential equation here has a unique solution. So we're going to use theorem 1.2.1. And first we need to write this differential equation in the standard form. So for that, we're going to write y prime equals y plus x over y minus x. And so this function right here on the right, this is my f of xy in the theorem. Okay, so if you recall in the theorem, we have to find out when f is continuous. Well, when is this function continuous? Well, as long as the denominator is not 0. In this case, that's the only problem that we could encounter. So that would mean that y not be equal to x. So any point is okay except those when y is equal to x. And the second thing we have to do is find or determine when the partial of f with respect to y is continuous. Well, first let's find out what that partial is. We'll do that here on the side. And for that, we think of x as a constant. We're going to have to use the quotient rule here. And so the derivative of the top, we're going to get 1 times the bottom function minus the top function times the derivative of the bottom, all over the bottom function squared. And so I get y minus x minus x. I get minus 2x over y minus x squared. Again, the only problem we could have it with this function is when y equals x. So the same condition applies so that the partial of f with respect to y be continuous. So we can see then now that the region is all those points, and I'm going to go ahead and visualize that, all those points in the xy plane, except for those when x is equal to y, which are these points on this line. So anything on this side, meaning any point right here, I can find a solution passing through that point. And the region is going to be the region of all those points x, y's in the xy plane, such that x is not equal to y.